to talk about biodegradability, you must define time, and you must define the environment, the disposal environment, like composting. All right? Partial biodegradability or degradability or will eventually degrade is not an option, and it has serious environmental consequences. So, if you want to define or design for biodegradability, which has got nothing to do with bio-based, then you must define for complete biodegradability. I'm going to go to the next slides, which basically tells you what biodegradability means. And I will not go into the details. You can read this at your leisure later. But in simple terms, biodegradability means complete consumption of your biocarbon product. And the key phrase here is define time frame and define the specified environment. So composting is one such environment, and you have ASTM specification standards, which I would refer you to look at these things. Right? So why is it important to make sure you have complete biodegradability? And this has got to do with the following fact, that if you allow degraded fragments to be released into the environment, it has been found that these residues, look at the third point in your slide, these plastics residues can potentially function as a transport medium for toxic chemicals in the marine environment. So you don't want to make your plastic product or your bioplastic product degradable. You want to make it completely biodegradable and removed from the environment so that it doesn't have any problems. Or you make it recyclable, or you collect it and go to a waste to energy, but you don't want to simply degrade it and simply have it released into the environment. And there are these references which is listed on that slide, which brings to you these points of how the toxins are carried through. All right? Let's go to the next slide, and this is just another picture of how, if you allow fragments, that it can be colonized by microorganisms, it picks up toxins, and it can be transported up the food chain. This one is a paper published by Thompson in Science, and the basic take-home message, you can read this in your leisure, is the following, that minute fragments of non-degradable and parts of biodegradable plastics, if it is not completely biodegradable, has found its way into the guts of some marine animals and therefore cause problems. The take-home message of all of these slides is that you must ensure complete biodegradability meeting ASTM standards, all right? And bio-based has got nothing to do with the end of life. So when you design for biodegradability, when you design for bio-based, and this slide captures it, so let's pay special attention here. If you want to make single-use, short-life, disposable products like packaging, then you will design for biodegradability. It could be designed for biodegradability of a synthetic plastic product as well as a bio-based plastic product. But it is for an end-of-life option. Okay? Biodegradability is an end-of-life option. Bio-based, on the other hand, is for durable products. So if you want to make a computer casing, an automotive part, any number of durable products, a phone which can be easily collected, then you will use a bio feedstock, and the value proposition there is to reduce the carbon footprint, where biodegradability may not be a required element for reasons of performance, safety, and long product life, but you must specify an alternative method of disposal. That needs to be identified. Okay? That's what you have there. And examples of bio-based products which are durable and not biodegradable are the biopolyurethanes. You've heard of the John Deere panel tractors being made out of a bio-based resin. That's not biodegradable. biofiber composites. They're not biodegradable. And the recent announcement of making biopolyethylene from sugarcane. That's also not biodegradable. The value proposition for each of these products is the fact that it is made from a biorenewable feedstock, which allows you to reduce the carbon footprint of your product. That is the value proposition and not biodegradability. Okay? Now, this value proposition is now being adopted, and something which may be of value to you, that the federal government has now a regulation, a law, which requires them to buy bio-based products. And on your slide, you see the website address, www.biopreferred.gov. That website will tell you all about the bio-based products which they are procuring or will be procuring soon. There are the regulations listed there. The point I want to make here is that in that procurement by the federal government, which allows, according to them, to provide the market pull for these products, that you must define biocontent, and it uses the ASTM 686 standard, which I just explained to you before. You must also do a LCA, report on an environmental profile, and we have an ASTM standard there. And where required for biodegradability, you must use ASTM D6400. You must also have performance requirements and assurance that the products are available. So, just to let you know that the federal government has basically implemented the concepts and guidelines and the standards I've just described to you, and they provide you a marketplace. Okay, so if I summarize this to you, I want to tell you that you will be able to report, and I think every product will soon have to do this, is to report on the carbon and environmental footprint of products. The ASTM standards are there, and hopefully you have an understanding of why bio feedstocks allows you to reduce your carbon footprint. It potentially has the value proposition to reduce your environmental profile as well. Now, in the next set of slides, I'm not going to cover this. I just put it in here because of time constraint, but suggest to you that in order to report the total environmental footprint or total profile, you need to use life cycle assessment tools. And the slides which have been presented and made a part of this presentation sort of walks you through how an LCA is done. All right, that's a total subject of another presentation. But what I like to do is close it around here, summarize to you that biofeedstocks offer you a value proposition for reducing your carbon footprint, that biodegradability is an end-of-life option, that if you want to engineer biodegradability, you want to make sure that it is completely biodegradable, and you define time and disposal environment for it. And at this stage, I'll stop here and take questions through Elizabeth. Elizabeth, you can come online.
Great. If you have any questions at this time, please press *8 on your telephone. And while we're waiting for questions, I'll just remind everybody that you can download the PDF of the presentation using the icon at the top. It's the handouts icon, and it looks like 3 white sheets of paper. So once again, if we have any questions at this time, please press *8 on your telephone.
Can I be heard here, Elizabeth, by everybody?
I'm moving our first question into conference.
All right, just so that to all these attendees here, if you have any questions after this and you feel that you need to send it to me, I think my email address is right on that first slide. It's my last name, Narayan, @msu.edu. Feel free to shoot me an email. If you want to you leave your telephone number and say, call me, I want you to explain this better or whatever, I'll be happy to do so. Just wanted you to have that information.
Okay, great. And with that, our first person asking a question is on the line. Go ahead, speaker.
Hello. Thanks for your presentation. I have a question regarding one of your early slides that compared the carbon footprint, the CO2 released per 100 kilograms of plastic, comparing PLA versus PET versus polypropylene.
Yes.
And just to clarify, does that assume sort of the ideal condition where the PLA is broken down completely for each cycle?
Yeah. Can you see that slide up front in front of you? Elizabeth, are they able to see that slide? I put it up here.
Yep, they'll be seeing slide 8 right now.
Okay. The concept there, you're right. It assumes that all of the PLA is broken down. In other words, the PLA is either burnt to give you CO2, or it is put in a composting to go to CO2, or any other option. It goes as CO2. Then intrinsically, if you plant another crop, then that CO2 is fixed. It does not take into account the carbon emissions and carbon energy used in the conversion of the feedstock to PLA product or further products. You follow what I'm saying there?
Yes, which was one of your later slides.
Yes. And the fossil, what I'm saying there, and I hope this is a key point you made, it's a very good question. In the case of polypropylene, for example, since the carbon has been conserved being created over millions of years, and we use it and put it back, I do not fix it right away. I'm going to take another million years to fix it in that cycle which I showed you. Therefore, when I, again, burn CO2, burn the polypropylene, or do something which is, because these will not stay forever, even in a 1 to 10 year time frame, it is going to completely break down. That CO2 is going to be released, but we are not going to be able to fix that. That's the concept.
So translating to the real world, in my field, my name's Jim Hill with the Department of Conservation in California. The comparison is being made between PET bottles and PLA bottles. The ideal situation would assume basically that all those PLA bottles that enter the marketplace would have to be in some way composted or returned to the carbon cycle.
Correct. And one addition to that which is being offered, as you probably know, is that PLA, like PET, can be recycled. And that's where the dilemma or the issue has come up. For example, if you took PLA bottles and you recycled it back to lactic acid, you can make PLA again, similar to what PET is being done. So the value proposition for recycling PET, for example, is that using that same slide which is in front of you, instead of simply allowing that carbon in the PET to go out as CO2, I'm using it to make another bottle, thereby not using fresh carbon, which again I put out as CO2. So I am conserving the carbon, but ultimately it will go out. In the case of PLA, whether you burn it, or you compost it, or you recycle it, you'll still be intrinsically at the zero carbon footprint, except for all of the carbon energy and the carbon emissions which you're using to convert it.
I see. Thank you very much.
Okay, great. Do we have any other questions? I'll move on.